There is a prescription that follows grief almost everywhere. Get moving, exercise, go to the gym. And the people who say this are not wrong. There is documented physiology behind the recommendation. But they are not giving you the most precise version of what is happening. And the difference sits inside a specific piece of neuroscience that almost nobody explains clearly. The body of someone who has lost a person they loved is not a healthy body under temporary stress. It has been reorganized neurochemically, hormonally, and autonomically around an absence that it registers not as an idea but as a threat. The HPA axis, which is the hormonal alarm pathway running from the hypothalamus to the pituitary gland to the adrenal glands, has been engaged in a way that more closely resembles sustained exposure to physical danger than ordinary sadness. Cortisol levels in bereaved individuals are measurably elevated for months after a significant loss. In documented cases involving the death of a spouse or child, that elevation persists for years. The sleep architecture fractures along specific and predictable lines. Inflammatory markers rise. The cardiovascular system responds. Into this reorganized body, the prescription is go to the gym. And the gym does something. Brain-derived neurotrophic factor, BDNF, the protein that promotes neural plasticity and supports the structural integrity of the hippocampus, increases with sustained aerobic exercise. Endorphins rise. These are real documented mechanisms with real significance, but there is a problem that sits underneath all of them, and it has to do with what the bereaved body specifically needs at the level of the autonomic nervous system, and why 11 minutes of cold water per week produces a response that an hour at the gym approaches much more slowly, if at all. In 2022, Dr. Susanna Soberg and her colleagues at the University of Copenhagen published a study in Cell Reports Medicine. They measured the catecholamine response, the body's production of norepinephrine and dopamine, in healthy adults undergoing structured cold water immersion. The finding was not subtle. 11 minutes of cold water per week, distributed across multiple sessions, produced a norepinephrine increase of approximately 250% above baseline. Dopamine rose by a comparable magnitude and remained elevated for several hours. These are not the numbers associated with a moderate workout. These are the numbers associated with a rapid, disproportionate recalibration of the brain's entire catecholamine signaling environment. The question the Soberg study was not designed to ask, but which the grief neuroscience literature allows us to ask, is what that recalibration means for a body already running on the altered neurochemistry of loss. To understand the answer, you have to go to the skin. Your skin contains thermoreceptors, specifically a protein channel called TERPM8, transient receptor potential melastatin 8, which functions as the primary molecular sensor for cold at the cellular level. When skin temperature drops below approximately 10 degrees Celsius, TRPM8 channels open across the surface of specialized sensory neurons. An electrical signal fires. It travels along unmyelinated C fibers and thinly myelinated A delta fibers, ascending through the spinal cord toward the brain. The signal reaches, among other destinations, the locus coeruleus. The locus coeruleus is a small paired nucleus in the dorsal brainstem, the brain's primary manufacturer and distributor of norepinephrine. Its axons project throughout the entire cerebral cortex, the hippocampus, the amygdala, the thalamus, and the spinal cord. It is structurally the brain's alerting and regulatory infrastructure. When it fires in response to cold, the effect is not localized. It is broadcast across the entire system. Attend, come back, recalibrate to the present moment. Dr. Mary Frances O'Connor, who directs the Grief, Loss and Social Stress Laboratory at the University of Arizona, has spent more than a decade mapping what happens to the living brain during bereavement. Her research, published in journals including Neuroimage and Psychological Science, documents a consistent pattern. The default mode network, the brain's self-referential processing system, active during mind-wandering and autobiographical memory, shows elevated and dysregulated activation in bereaved individuals. The bereaved brain is frequently not present in the moment it is occupying. It is running rehearsals of the past, scanning for a person who no longer occupies the expected coordinates. The prefrontal cortex, which normally modulates and suppresses the default mode network when external attention is required, shows reduced regulatory capacity in her bereaved subjects. Norepinephrine at the appropriate concentration is one of the primary molecular signals that restores prefrontal regulatory capacity. The locus coeruleus through cold-triggered firing does in 11 minutes something that a treadmill takes considerably longer to approximate, and which, in the specific context of grief's cortisol load, the treadmill may be working against in ways that have not been sufficiently acknowledged. A careful distinction matters here between what is clinically confirmed and what is mechanistically plausible, because collapsing that distinction is one of the ways scientific-sounding explanations become unreliable. What is clinically confirmed? Bereavement elevates cortisol. This is documented across dozens of studies in Psychoneuroendocrinology, the Journal of Clinical Endocrinology and Metabolism, and biological psychology mean cortisol levels in the first 6 months of spousal bereavement can be 20 to 40% above age-matched controls. What is also confirmed, sustained moderate intensity aerobic exercise elevates cortisol during the activity. In a healthy individual, this spike is adaptive. What is mechanistically plausible rather than confirmed? That in a body already carrying chronically elevated cortisol from bereavement, whose HPA feedback axis shows reduced glucocorticoid receptor sensitivity, the additive cortisol load of sustained exercise may attenuate the expected benefits in ways specific to this population. The assumption that the bereaved body will respond to exercise exactly as the healthy body does is not supported by the endocrinology. Cold water creates a different stress signature. The sympathetic activation is brief, intense, and rapidly resolved. And what follows is what is called the vagal rebound. If what this channel has given you is a framework you could not find explained anywhere else. I've spent months building a companion called What Feynman knew about grief. It extends and collects everything this series explores. The link is in the pinned comment below. Stay with me, because the mechanism most people find hardest to believe isn't the norepinephrine surge itself. It is what the nervous system does in the minutes after the cold ends, why the bereaved body, specifically, may find something in that moment of physiological stillness that no measure of exertion produces. The vagus nerve originates in the medulla oblongata and descends through the neck, chest, and abdomen, innervating the heart, lungs, liver, and gut. It is the primary neural corridor of the parasympathetic nervous system, the system that governs rest and the body's return to baseline after activation. When you exit cold water and begin to warm, the sympathetic surge does not simply stop. The body shifts toward parasympathetic dominance. Vagal tone increases. Heart rate variability, the variation in time between successive heartbeats, rises. Heart rate variability is one of the most direct non-invasive indicators of the functional state of the autonomic nervous system. High heart rate variability signals parasympathetic engagement. The body is not running its alarm system. Low heart rate variability signals sustained sympathetic dominance. The system cannot disengage from alert. Dr. Richard Lane and colleagues at the University of Arizona, in work published in Biological Psychology, documented reduced heart rate variability in bereaved individuals compared to non-bereaved controls. The bereaved autonomic nervous system carries the measurable signature of a system that cannot return fully to rest. This is autonomic dysregulation, not a psychological failure, but a structural and measurable shift in nervous system calibration. The vagal rebound following cold water immersion produces acute improvements in heart rate variability that appear in the available literature to be disproportionate to the brevity of the exposure. A 45-minute run also produces post-exercise parasympathetic recovery. This is real. But the magnitude from cold per minute of intervention is significantly larger. And in a body carrying the autonomic load of bereavement, that disproportion matters. There is a third mechanism that connects cold water to the bereaved body specifically. It involves the anterior insula. The anterior insula is buried within the lateral sulcus of the brain. Its function is interoception, the brain's representation of the body's internal physiological state. Pain, temperature, hunger, the felt sensation of your own heartbeat. All of these reach conscious awareness through the anterior insula. Dr. A.D. Craig, in foundational work published in Nature Reviews Neuroscience, described it as the site where the body's current condition is transformed into something the mind can sense and name. Grief is registered in the anterior insula. Dr. Naomi Eisenberger at the University of California, Los Angeles, whose research on social pain has been published in Science and Social, Cognitive and Affective Neuroscience, demonstrated in a series of neuroimaging studies that social loss, separation, rejection, and the permanent loss of an attachment figure activates the anterior insula and the dorsal anterior cingulate cortex. These are the same regions activated by acute physical pain. The overlap is not metaphorical. The brain processes the loss of a person using the same neural substrate it uses to process a burn. When the bereaved describe grief as feeling like a wound, a heaviness in the chest, a structural sense of damage, the anterior insula is the anatomical reason that description is precise rather than poetic. Cold thermoreception terminates, among other places, in the anterior insula. The TRPM8 signal pathway delivers its input directly to the same interoceptive network that grief has occupied. Cold water immersion does not simply produce catecholamines. It delivers a competing, controllable, intense physical signal to the precise neural substrate that loss has organized around absence. The anterior insula, running the interoceptive signal of a missing presence, receives an acute thermal input through the same architecture, a present tense physical fact interrupting the continuous signal of what is no longer there. This is mechanistically plausible rather than confirmed in bereaved populations specifically. The direct study has not been completed, but the anatomy is verified, the pathway is verified, and the logic of why a stimulus that activates grief's neural substrate through a present tense sensory channel produces a different effect than one that does not is coherent with everything the interoception literature has established. The companion resource connects all of this. What Feynman knew about grief is in the pinned comment below. I'll take it only while this video is running. There is one more mechanism, and it runs through sleep, which is where the damage from grief accumulates most consequentially over time. Grief fractures sleep. Studies in psychosomatic medicine and sleep medicine reviews document that bereaved individuals show specific, replicable disruptions in sleep architecture. The most consistent finding is a reduction in slow-wave sleep, the deep non-rapid eye movement phase associated with physical restoration and hormonal regulation. Bereaved individuals show increased sleep fragmentation and reduced total sleep efficiency. Dr. Michael Perlis and colleagues at the University of Pennsylvania's Behavioral Sleep Medicine program documented that the chronic sleep disruption of bereavement involves specific dysregulation of the homeostatic sleep drive, the biochemical pressure that should accumulate during waking and compel sleep. The bereaved body, despite exhaustion, frequently cannot generate the sleep architecture that exhaustion should produce. The slow-wave sleep reduction matters because of what happens during that phase. Dr. Micah Nadergaard and colleagues at the University of Rochester described, in a landmark 2013 paper in Science, the glymphatic system, a waste clearance network in the brain that operates primarily during slow-wave sleep. Cerebrospinal fluid is pumped through channels surrounding the brain's blood vessels, flushing metabolic byproducts, including tau protein, amyloid beta, and the chemical residue of sustained neural activity, out of the brain tissue. The glymphatic system is the brain's overnight clearance operation. When slow-wave sleep is disrupted, that clearance is impaired. The metabolic waste of a full day of neural activity remains. Everything this series has documented about the bereaved brain: the default mode network, the anterior insula, the cortisol load, the fractured sleep. The companion guide pulls it into one place. What Feynman knew about grief is in the pinned comment below, only while this video is running. In the context of bereavement, which sustains high-intensity activation across the default mode network, the anterior insula, the prefrontal cortex, and the amygdala, all running simultaneously, the glymphatic burden is not abstract. The bereaved brain generates substantial neural metabolic waste and loses the primary mechanism by which it is cleared each night over weeks and months. This accumulation contributes to the cognitive fog, the difficulty concentrating, the sense of mental heaviness that bereaved people consistently report, and that is too often attributed to psychological distress alone. Cold water immersion has a documented effect on slow-wave sleep. A 2018 meta-analysis in Applied Physiology, Nutrition and Metabolism found that post-immersion cold water exposure improved sleep onset latency and slow-wave sleep duration. The mechanism is thermal. Core body temperature drops post-immersion, and the subsequent rewarming produces a temperature trajectory that mimics the evening temperature decline the circadian system uses to initiate slow-wave sleep. The body, warming from cold, receives a signal that its sleep initiation architecture is calibrated to recognize. The gym, followed by a warm shower, moves core temperature in the opposite direction. Not harmful, but the thermal after-effect of cold is specific. It speaks to the circadian signaling that grief-disrupted sleep has interrupted. Before this video ends, thank you. Truly, YouTube removed our ad monetization. And even after that, they continue running ads on our videos, collecting that revenue while we receive nothing. We tried to remove the ads, the machine kept them running. So we created what Feynman knew about grief, not as a business move, as a way to keep this information reaching more people, without depending on a system working against us. If what you found here mattered to you, the link is in the description and pinned in the comments. That is how this channel stays alive. Just as cold water speaks to the nervous system in the nervous system's own language, brief, precise, and unignorable, so does this channel keep making the videos. All of the mechanisms taken together describe something larger than a comparison between cold water and exercise. They describe a body that has been reorganized around an absence it registers as physical fact. The locus coeruleus, depleted by chronic stress, receives a signal large enough to recalibrate its output. The anterior insula, running the interoceptive signal of a missing presence, receives a competing thermal input through the same substrate. The vagus nerve, whose reduced tone is the autonomic signature of a body that cannot stand down, rebounds into parasympathetic dominance. The slow-wave sleep that glymphatic clearance requires receives a thermal after-effect the circadian system recognizes. Each of these mechanisms acts on the body in grief at precisely the level where grief has already reorganized it. Not above it, at the level of meaning, or memory, or narrative. At the level of the receptor, the nucleus, the nerve, the temperature, the body does not grieve as an abstraction. It grieves as a physical event, through specific structures and specific pathways, with measurable alterations in chemistry and calibration. The elevated cortisol is not a malfunction. The dysregulated default mode network is not weakness. The reduced heart rate variability, the anterior insular running loss as an interoceptive signal, the fractured sleep architecture. These are the marks of an attachment that was real, measured in the body's own units. Cold water does not erase those marks. Nothing does. What it does is speak to the nervous system with enough precision and enough intensity that the system can briefly hear something other than its own alarm. For the duration of the rewarming, for the vagal rebound, for the fragment of slow-wave sleep, the thermal cue helps restore. The body is not separate from the loss. It is the instrument on which the loss plays. And sometimes the only signal that reaches that instrument is one cold enough to cut through everything the alarm system has built around it.